Morning, AP Chem. Today we're going to be doing 6.9, which is the last section in Unit 6, which is about Hess's law. So we're going to be calculating the change in enthalpy for a reaction using Hess's law. And remember before, we talked about that there are 4 methods for finding the change in enthalpy. The previous 3 we have gone over before, finding it through calorimetry experiments, calculating it using average bond enthalpies, and then using enthalpies of formation. So today we're going to talk about how we calculate it using Hess's law. So Hess's law basically states that if a reaction is carried out in a series of steps, the overall change in enthalpy will be equal to the sum of the enthalpy changes for the individual steps. So since the heat that is, or energy that's contained in the reactants is constant under similar conditions of pressure and temperature, and the heat in the products is also going to be constant under pressure and temperature, the heat or lost or gained going from reactants to products should also be constant under that same pressure and temperature. So basically, the path that you take or the number of steps that you take shouldn't matter in terms of the change in enthalpy going from reactants to products. So basically, there are a lot of theories about how reactions take place, and you can predict the steps that happen, but in general, for those steps, the change in enthalpy should be the same no matter what, since your energy in products is constant, your energy in reactants is constant. The change between them shouldn't be different between whatever steps that you are taking. So the best way to go through this is just to do examples. And I'm trying to move my face out of your way. So here we want to calculate the change in enthalpy for the following reaction using the information in the table below. So we're given 2 reaction types and their enthalpy change. Basically, what we want to do is use these 2 reactions, add them together to make this overall reaction. Okay, so these are the only 2 reactions we will be using, and we'll be using the enthalpy changes for those reactions. Now remember, we can basically multiply these equations or divide these equations, and we can also reverse these equations. But whenever we make a change to the chemical equation that we're using, we also make a change to the enthalpy change value that we're using. So if we reverse it, we have to reverse the sign of delta H. If we double it, we have to double the value or magnitude of delta H. So we're going to be considering that first equation that they gave us. Comparing it to the final equation that we're working for, what do we have to do? We have to basically multiply reaction 1 by 2. Why do we do that? Our final equation, if you look, contains 2 moles of N2O5. The equation that was given to us in reaction 1 only had 1 mole of N2O5. So that's why we decide to multiply this reaction by 2. When we multiply that reaction by 2, we also have to multiply the delta H by 2. Now let's consider the second equation. What do we have to do for the second equation? First thing you might notice is that NO2 is on the product side. We need it on the reactant side. So the first thing I definitely want to do is flip that equation. Show up. So I flip that equation to get NO2 on the correct side. I also need to multiply the reaction by 2. That way I know I can cancel out the NO that was given from reaction 1, which I don't need in the final products. Okay, so my goal here is to not only get my reactants and products with the correct coefficients, but to also cancel out those intermediates that I don't need in my final equation. So now I can go through and see what cancels. Also, when I flipped it, I have to flip the sign of delta H, so that's where this negative comes from, and I also multiplied it by 2, which is where that 2 comes from. So now I can see, well, what's going to cancel out, and will it give me to my final equation? These are all going to end up canceling out. What you will notice is that the coefficient for O2 is going to basically go from going from 3 to 1. because I only canceled out 2 of those O2s with this equation. I canceled out all of the NO, which is great because I don't want any of it in the final equation. So my final equation, once I add these two things together, is going to be 4 NO2 gas plus 1 O2 gas, yielding 2 N2O5 solid. And then to find that delta H, all I have to do is sum together these two values, and I get negative 219.0 kilojoules. You also have to pay attention, are these values in kilojoules or joules? So with the data that they give you in that first chart, be sure that all your units are the same. Don't just add them together and ignore the units. If one of these was in joules, I would want to change it to kilojoules so that I can just add them all straight together. So next we have another example, because again, the best way to learn this is just do some problems. So again, this message always pops up. If I ignore it, everything works out fine. Again, I want to calculate delta H for the following reaction using the information given in the table. This one, you'll notice, is a little bit more complex because I have 3 reactions given in the table. I am going to end up using all 3 of these reactions. Just because they give me 3 doesn't necessarily mean that I will use all 3, but in this case, I will be using all 3. So this again is our final equation. Sometimes I like to write that out from the start just to make sure that I'm adding together the correct thing. So I didn't set up this one that way, but that is a strategy if you want to try to use it. So I'm just going to consider these reactions in the order that they're given to me. So there's that. I didn't mean to show you that all the way. Just ignore it. It's fine. This is the overall equation. For reaction 1, what can we use that is useful in there? Really, the only thing useful for us is going to be the H2 gas. So I'm going to be focusing on the H2 gas in equation 1. Since our final equation has 4 moles of H2 gas and the equation given only contains 2 moles, what I'm going to end up doing is just multiplying that first reaction by 2. So I do want H2 on the reactant side, so I don't need to flip the equation. And then since I multiplied the equation by 2, I'm going to multiply my delta H also by 2. Looking at the second reaction, what changes do we need to make in terms of coefficient or flipping the reaction? The good thing that we want from this reaction is the C3H8. On our overall equation, we want C3H8 on the product side, but this reaction is given on the reactant side. So I want to flip reaction number 2. The coefficient for C3H8 is the same. It's 1 for both of them, so I do not need to multiply by any given number. All I need to do is flip. So I'm going to multiply reaction number 1 basically by -1. Sorry, reaction number 2. So that flips this reaction to get C3H8 on the product side. And then I will also have to flip the sign of my delta H, which originally it was exothermic with a negative delta H. Now it's going to be endothermic because -1 times negative is going to be positive. Okay, things to consider. I see that my O2s are starting to kind of cancel out because I do not have O2 in the final reaction. So with all 3 reactions, I do want O2s to cancel out. So that's going to be something to consider. My dog is snoring, which is just so rude. I think this is interesting. So I'm going to want to end up canceling my O2s out, which is something I want to consider when doing reaction number 2. I also see this CO2 that I am not interested in. So I will also want that to cancel out when I add in reaction number 3. My H2Os, which are not in the final equation, do cancel out, so that is a good thing to consider. So then looking at reaction 3, which is C solid, O2, carbon solid plus O2 yielding CO2. I do want my CO2s to cancel, so I would want a coefficient of 3. I also want a coefficient of 3 for my O2, because right now I have this 2 canceling out this 5 to be 3, so I would want 3 O2s on the reactant side. So what I'm going to end up doing is multiplying reaction 3 by 3. Don't need to flip the sign or anything like that. Since I multiplied the reaction by 3, I have to also multiply the delta H by 3. So that will cancel out all the unnecessary things I do not want, which is wonderful. And I can add together my delta H's to get the final delta H of the equation, which is negative 103.8 kilojoules. And again, all my units here are in kilojoules, so I'm safe to just add those all up. Then you could also be given this kind of information. Use the enthalpy formation values to determine the heat delta H of the reaction for a reaction between carbon solid and Fe2O3, so iron 3 oxide, to produce iron solid. So I'm given these two equations, but I'm not given the overall equation. So I like to kind of start from the end and then work my way there. So I'm going to kind of write out a balanced equation for what I would expect to happen between carbon solid and iron 3 oxide. So carbon solid and iron 3 oxide are going to be my reactants. I know one product is going to be iron solid based on the information given here, but then I also need a product that has oxygen and carbon. And based on this information that I'm given here, looks like it's gonna, like CO2 solid would be a fine candidate for that because it has both carbon and oxygen. So my overall equation, I didn't want to exit. Spoilers. Oh my lord. Oh my lord. I love technology. So my overall equation is going to be iron 3 oxide plus 3 carbon solid, yielding iron and CO2. And these coefficients I just use through balancing the equation, making sure I have the same number of carbon, oxygen, and iron on the same side. So now, with my end goal in mind, I can kind of figure out how I need to basically what I need to do to those equations to get my overall final reaction here. So for the first equation, you'll notice we have 2 iron solid, O2, and iron 2 oxide. In our overall equation, we want iron 2 oxide on the reactant side, and we want iron solid on the product side. So I know the first thing I want to do is flip this equation. I also need to change coefficients. Notice I want 4 iron solid and I want 2 iron 3 oxides. So that tells me, given these stoichiometric coefficients here, I want to multiply everything in this reaction by 2. I also like multiplying by 2 because that's going to get rid of that 3 halves O2, which is nice. So I'm just going to multiply that first reaction by negative 2. That means I also have to multiply the enthalpy of this reaction by negative 2. Negative from flipping it and 2 from changing the coefficients. The second reaction, I have carbon solid where I want it on the reactant side, and I have CO2 where I want it on the product side. I do not have O2 in my overall equation, so I'm definitely going to want to cancel that out. So I want to see, okay, will a 3 coefficient help me here? Because I have 3 coefficient for O2 here. And it would, because in our final equation, we also have 3 carbon solid, and we also have 3 CO2 solid. So I'm going to just multiply the second reaction by 3, which means I multiply my delta H by 3 as well. So if I do my multiplication and add them up here, I get a delta H of positive 462 kilojoules. So this is an endothermic reaction. It takes some energy. Okay, so that is the fourth way we can calculate delta H for a reaction. You can again use enthalpy of formation or just enthalpy of an overall reaction, but it's the same method here where we are just kind of manipulating equations to get the final step here. And these steps could be different. These are just proposed steps. You could use them with different equations that would hopefully yield the same result because, again, your change in energy from reactants and products shouldn't be different because your reactants are going to have the same energy, your products are going to have the same energy. It's just how you get there. So it's kind of like a roadmap. You can take the highway or you can take back roads. Either way, you're getting to the same place, just with different steps. We do have a worksheet that goes with this section. So that is posted on Classroom if you haven't already seen it. Go ahead, print it out, work on it, and have a wonderful day.